All right. So we are going to start now. Are you ready? Sure.
Okay, can
Yes.
everyone hear me?
We
You
we are
can
going
see
to
the
start
slide?
now the talk by Joel Hutchinson from the Institute from the Polytechnical Institute of Paris and the school. And thank you very much. So it's yours.
Okay, yeah. First, let me thank the organizers for this workshop. It's been certainly very informative and helpful for me, and I'm happy to present some of my research here. So today I'm going to take a little break from QMC and focus on some unusual aspects of topology. And this is work I've been doing with Chern at École Polytechnique. So we propose a new fractional invariant that has some connections with entanglement. You can find the details on the archive here. So that's good. Everyone can hear me. It's okay.
Yes, it's all right.
Good. So first I'll go through some of the line of reasoning that led us to propose this invariant. Then I'll focus in some detail on a particular two-spin model that gives rise to some unusual physics. And then we'll see how this gets generalized to other spin models. And then finally, how it appears in electrons on a honeycomb lattice. Okay, so to start at the most basic level, you can open any textbook that has a section on Berry phase or Berry curvature. So for example, Grunewig's TI book, and you'll find this simplest example of topology, which is a spin 1/2 in a radial magnetic field. So the magnetic field sweeps out this sphere in parameter space, and you have this two-level system where if you look at the spin expectation value for the ground state, you find it rotates across the sphere, and that reflects the presence of a degeneracy monopole at the center of the sphere. So there's a topological charge here that the spin responds to in the manner of Gauss's law. And so mathematically what that means is we have this Berry connection defined, which is a derivative over this parameter space of the ground state. You have the Berry curvature, which is a derivative of the connection. In this case, it's just sine theta over 2. And then if you integrate that curvature across the whole manifold, you get the Chern number, which is just +1. And that +1 is indicating the single charge at the center. Okay, so a few years ago, Chern and one of our students were looking at this in the context of sweep protocols, so some time evolution for a qubit system. And what you find is that it's very simple to measure the topology. So if you sweep a magnetic field from north to south, you don't need to access the full spin texture of the sphere to get the Chern number. You can in fact just measure the spin expectation value from 2 antipodal points. And that's enough to recover C. Okay, so this has been done experimentally by the group at Santa Barbara, who are now at in Google's artificial intelligence quantum team. And so they did this not just for 1 qubit, but for 2 qubits with some transverse coupling between them. And so this is their experimental result. So they've probed the phase diagram for this 2 qubit system as a function of the coupling on the x-axis here and the magnetic field on the y-axis. And you find these 3 distinct topological regions: Chern number 0 in blue, Chern number 1 in green, and Chern number 2 in red. And those 3 phases reflect either having 2 monopoles in your parameter space, 1 or 0. Okay, so we looked at this result and sort of said, well, if the thing that they're measuring for these experiments is an individual spin, even in this interacting system, then shouldn't there be some topological quantity that corresponds to each spin independently? And it turns out that there is. And the way that you uncover it is by doing what's really the most naive thing. You take the definition for the Berry connection and you stick a index j for the jth spin on it. Okay, so now the definition here is that you're taking a partial derivative over the parameter space that corresponds to the Hilbert space for just the jth spin. Okay, so you have to check that this is a sensible thing to do, that this operation is actually well defined. And it turns out it is in the cases that I'm showing you. And then from that, you define a barrier curvature, and you integrate that to get what we call Cj, this partial Chern number. So it's like a Chern number corresponding just to the jth spin. And indeed, that satisfies the same relation we saw before. You can simply measure the jth spin at two antipodal points and recover this number. So there's a lot of checks you have to do to make sure that this is a good thing to do. So it has to be a well-defined operation. The result you get for Cj has to be gauge invariant. So the connection is not gauge invariant, but you can indeed prove that Cj is. And it also has to be topological in some sense. So you have to check that it's robust to symmetry preserving deformations. Okay, so I won't go into detail into any of these proofs, but I will give you some evidence that this is indeed a robust quantity. So let's start by looking at a very simple example of a model that might give us some unusual physics in this case. So we have two qubits. We have sigma 1, sigma 2. They're both in these radial magnetic fields, but now we're going to allow for the addition of some offset Zeeman field in the z direction. So that m could be the same or could be different for these two spins. And then these two spins are going to interact via some Ising interaction, and will allow that coupling constant to depend on theta as well. And the question we actually want to know is does this model give rise to this kind of situation that we find here? And I'll explain why this is a special situation. So what we have here is a product state at the North Pole. So essentially the magnetic field is the dominant contribution at the North Pole, and you just have both spins up. And then at the South Pole, you want a degenerate antiferromagnetic configuration. So you want the interaction to be the dominant thing at the South Pole. And the reason is because if you can engineer this kind of configuration, then in time evolving from north to south, there's only one state that is adiabatically connected at the South Pole to this product state at the North Pole. And that state is the entangled Bell state. So let's see if this actually happens in the model. So we do this numerically, just time evolving the system. So we fix ourselves along some constant meridian phi. And then we vary theta linearly in time with some sweep velocity v. And what I'm showing here is some examples where we have different offset fields between the two spins. And what you see is that at weak coupling, so small r tilde, you just have two copies of what we had on the same slide. So you essentially have two independent topological systems. A spin makes a full rotation around the sphere. At some intermediate coupling, what you find is the second spin no longer makes the full rotation. That's the one with the higher offset field here. And then as you go to even stronger coupling, both spins will become trivial, and this becomes a totally trivial system. The interesting case happens when you fix the two offset fields equal to one another. And what happens is exactly what we saw in the previous slides. So you have a product state at the North Pole, and then at the South Pole, the spin expectation value vanishes completely. And that reflects this entangled Bell state. Okay, so we can compute the Chern number from these results using the formula from the earlier slide. And what you see is that the Chern number, as you increase the coupling, goes from 1 to 1/2 for both of these two spins. So this is just an example with a constant interaction and equal offset fields. And so the different colors here, we're showing different sweep velocities, and you can see that the transition becomes smoother and smoother as you go to higher velocities. That doesn't mean that we're accessing a continuum of Chern numbers by any means. There's still a well-defined unique Chern numbers. It's just that you start to get an infiltration of the very high excited states, and you're essentially measuring an average of the Chern number of the lowest bands and the higher bands. And so it turns out there's a nice analytic description of this non-adiabaticity. So these dashed curves you see here are an analytic result that come from some very old work by Landau, Zenner, and also Majorana. And what they were interested in were diabatic transitions in the two-level system. So you take a two-level system that with a dispersion like this, as a function of some time-dependent parameter. And the question that they asked was, as you take t to infinity, so you go infinitely far along this x-axis, what's the probability that you end up in either of these two states? And it turns out that if you follow Zener's derivation, it's a very nice, very simple paper to read. You can use his result to extract time-dependent amplitudes at any finite time. And it might not be obvious what the connection is to our model here, which is a 2-qubit model, so that's 4 states, not 2. But the key is that if you initialize the system in a product state at the North Pole, you decouple the singlet and triplet sectors, and one of the triplet states becomes very high energy, and so you're left with a low energy system that's very well described by this 2-band physics. And so you can use these results to directly write down an expression for the Chern number, which is a function of the gap delta and some adiabaticity parameter gamma. And then you can do this for a non-constant interaction. So here, as a function of r tilde f of pi over h, you find that these are, there's a universal curve to describe this transition. And you can really get creative with the different kinds of couplings you choose. And you'll always get the same result modulo these small deviations that occur in the numerics from the infiltration of those high excited states. So we mapped out the phase diagram for this model as a function of the coupling r tilde along the x-axis here, and then one of the offset fields m2 on the y-axis, fixing m1. And you get a region where both Chern numbers are 1. So there, the topological charge is located within both of the parameter spaces corresponding to each spin. You have regions where only one of the partial Chern numbers is 1, so the topological charge is just in one of these deformed spheres. And then this trivial phase where it's outside of both of them. And this kind of geometric description breaks down precisely along this line of symmetry where both offset fields are the same. And there, the only way that you can envision this is that the manifolds are in a coherent superposition of containing and not containing this monopole. And that's where you get this Cj equals 1/2. Okay, so that might seem like a fairly fine-tuned model. So we need to check that this actually occurs more generally. And the first thing to do is generalize the interaction. So before we just had an Ising interaction. Now we're going to add some transverse coupling as well. And then the phase diagram for these models in this plane of couplings, what you see is that if the offset field is small, you have this extended region of Cj equals 1/2 that's in between the trivial and the topological phase. For larger offset fields, it forms a sort of an island within an otherwise trivial system. And then you can also set the offsets to 0 as long as you introduce some asymmetry via the couplings. And so in that case, you get all kinds of interesting phase diagrams. So you can have a half plane, for example, of Cj equals 1/2. And for these cases of the sign interaction, you have in fact 2 disconnected domains of Cj equals 1/2. So you might wonder, just for reference, why wasn't this seen in the experiment I pointed out in the first place? Well, unfortunately, they used a Hamiltonian that had an offset field just for one of the spins. So they violated this symmetry, and that prevents you from seeing this fractional Chern number. But we're talking with them now about how this can be realized. Okay, so those are 2 spins, but you can also go to higher numbers of spins. And the easiest way to do this is to just check what ground state you have at the South Pole in second order perturbation theory. Okay, so you can do that for all kinds of different configurations. So the first thing we did was we took 2 coupled versions, or 2 versions of the Ising model that we started with, and then added a perturbative coupling sigma x coupling between them. And what we find is that destroys this fractional phase. So you immediately have Chern numbers that are integer for all spins. But if you restore the exchange symmetry between these 2 sides by introducing a second X bond, you get back Cj equals 1/2. And then you can go to different numbers of spins. If you have 3 spins, you'll find Cj equals 2/3. And so just to summarize, the cases that we've checked, I showed you that two-spin Ising and XY models both have this Cj equals 1/2 region. It doesn't work for a Heisenberg model, but if you introduce some small anisotropy, you will recover Cj equals 1/2. And one of the key ingredients we find is inversion asymmetry. So you cannot do this if inversion symmetry is preserved. In these 4-spin examples, I showed you another important symmetry that arises. If you break an exchange symmetry, you will no longer get Cj equals 1/2, but if you restore it, you will. And then if you go to even larger numbers of spins, so a chain of an even-numbered chain of Ising coupled spins, you will always find a region of Cj equals 1/2. But if the chain has an odd number of spins, you in fact find a whole sequence of different rational values, n+1/2n. Okay, so in the remainder of the talk, I'm going to switch gears and focus on Dirac fermions on a honeycomb lattice, where we have some next nearest neighbor hopping in the form of a Haldane model. So we're threading a flux in this matter so that there's some topology in this system. And the reason for doing this is this nice mapping between the spin model that I showed in the beginning, or the sphere model, and the electrons on a hexagonal lattice. So the mapping follows this dictionary. You have a parameter space, which is a sphere in the first case that gets mapped onto the first Brillouin zone, such that the north and south poles are mapped to the k and k prime points. The radial magnetic field that we started with now describes the hopping elements, which have this Haldane flux. And so if we do this twice, if we have 2 spins or 2 spheres, then you can think of this either as a bilayer of Haldane models, or you can think of it as a model with 2 flavors of fermions. So either a spinless bilayer or a 2-flavor single layer. And I'll focus on the bilayer case for the rest of the talk. We showed that the Chern number for the sphere case takes this form in terms of the magnetization of the poles, and that indeed reproduces the Chern number that you get at half filling from the lower bands in the Haldane model. The mapping here is that sigma z gives you the sublattice magnetization in k-space, and the offset magnetic field, that Zeeman field that we started with in the sphere model, is a staggered chemical potential. So that gives you a Semenoff mass for the hexagonal lattice. And so now if we want an Ising interaction, that's sigma z, that corresponds to a density-density interaction, but it's an unusual one. It's one that's local in k-space. So this is something that's definitely worth studying. There's some very interesting recent papers to discuss these interactions that are local in momentum space and their effect on topology. But actually we'll do something much simpler in this case. We'll treat this density-density interaction as an effective interaction that arises from interlayer hopping. So if we have a bilayer system and we have some A to A and B to B hopping between the layers, then at second order in perturbation theory, you'll recover this kind of density-density interaction. And so all of that motivates this Bloch Hamiltonian here, where you have this standard notation for D vectors that represent the hopping. The M1 and M2 are the Semenoff masses, sigma are the Pauli matrices in the sublattice basis, and then the larger 2x2 structure gives you the 2 layers. Okay, so we compute the Chern number in this hexagonal model, and indeed it has qualitatively the same regions as for the sphere model. You have total Chern number 2, total Chern number 1, and total Chern number 0 regions, and as a function of the interlayer hopping. But we do not have a predefined formula for the partial Chern number in this case. So we have to ask if there are other observables that can illustrate the presence of this fractional invariant. And so the first thing to do is to look at this line of symmetry where we expect the fractional invariant to occur and see what happens to the band structure. So in this case, we develop, the gap closes right along this line, and you develop a nodal ring semimetal. So there's a nodal ring that appears right around the K prime point. So one thing we looked at was the transitions in the presence of circularly polarized light. The reason for that is some papers that have shown that you can measure the Chern number directly by the difference in depletion rates corresponding to positive and negatively polarized light when you excite this system at half filling. And so what we find is that the transitions appear exactly as in the regular Haldane model when you're near the K point, but near the K prime point, all transitions are completely forbidden. And so you essentially get a reduction of a half to the contribution to the Berry curvature in that sense. We looked at the entanglement entropy, so just taking the reduced density matrix over one layer. And what we find is that the entropy is 0 everywhere in the Brillouin zone, or in the reciprocal lattice cell here, except within the nodal ring region where it becomes maximal. Okay, so this shows us that there is a maximal entanglement occurring here at the south pole of this hexagonal model, just like we saw for the spins. And the ground state there is an equal superposition of occupying both layers and both sublattices. So you can look at the sublattice magnetization as well. You find that it goes from 1 to 0 as you go from K to K prime. And so if we go back to the dictionary, the sublattice magnetization gives us sigma z gives us a measure for the Chern number. And so this is a way to define the partial Chern number that indeed gives us what we expect. So if you're in the red region here, you have Cj equals 1. Along the gold line, you get Cj equals 1/2. And then along the green, you get Cj equals 0. We also looked at the edge states. So we just take a finite ribbon geometry here. In the trivial phase, you have no edge states. In the C equals 1 phase, you have 2 edge states at half filling. And then at C equals 2, you have 4. And then right along this line of symmetry, like I said, you have a nodal ring semimetal, so the bulk bands close, but you can still access these remnant edge states within the nodal ring. And then look at their current density, and you find that the current is split 50% between each of the 2 layers. Okay, so that's another interpretation for this Cj equals 1/2. Okay, so I'll just flash these conclusions. I tried to argue that there exists a gauge invariant and well-defined topological partial Chern number that describes each spin in an interacting model with radial magnetic fields. And that invariant can be rational valued as long as you have entanglement at just one pole. And then this is all dual to fermions on a hexagonal lattice, where you have other observables to take the place of this fractional Chern number. And I feel like I should leave off on a QMC note, and this will give me a chance to showcase some of the work that's come out of Würzburg. So you'll recognize many of the authors here present in the workshop. The model I just described to you on the hexagonal lattice, I talked about a bilayer system, but the same physics exists in the single layer Kane-Millet model. So you can ask, what happens to this system in the presence of interactions? So does that destroy the nodal ring, for example? It's an open question. And there's lots of work in this domain, right? So Poincare has this very important phase diagram established for the Kane-Millet model with Hubbard interactions, and that's using QMC. In our model, we require Semenoff mass. It's a crucial ingredient, and there are some interesting approaches to including this. So here's a recent paper where the Semenoff mass is generated dynamically in this Holstein kind of electron-phonon coupling, where you have some CDW instability that gives rise to this staggered chemical potential. And then you can also even implement the Kane-Millet model in the quantum spin Hall physics in an interesting color symmetric way that's been done in ALF, where the Kane-Millet term actually appears squared as an interaction term. And so I think I'll leave it there and take any questions.
Thank you very much. I think we're going to have some questions. Do we have some questions?
So this, I have a question. This phase diagram, if you have a bilayer system, you have this phase or this line where you have Cj equals 1/2. How would I mean, would this be stable under interactions? What if you put an interaction there? Will that remain, or is it something which can only be defined for the free case somehow?
Yeah, that's a very good question. So let me just put my headphones on here. Quiet. Yeah, so what we first of all, it's an open question. So we want to check that in an interacting model that this thing is actually preserved. But the prediction is that this fractional number Cj equals 1/2 is protected by the Z2 exchange symmetry. Okay. In the spin model, there's a Z2 exchange symmetry between the two spins, and the bilayer it's between the two layers. So as long as the prediction is that as long as your interactions preserve that Z2 symmetry, you should retain the same invariant.
Okay. Thank you.
Yeah.
So if there are no further questions, we can start our break and be back in about, let me confirm. Yes, in about half an hour with the talk, with the last talk on Fermat Monte Carlo by Farka. So thank you once again, Joel. And yeah, we'll be back soon.